All right, welcome to Stats. We're going to continue working on standard normal distributions and how we can use them to solve problems for us. So I have a problem already written up here. What we're going to do is we're going to call x the random variable for the SAT scores, and we're going to say that x has a distribution that is normal with a mean of 1010 and a standard deviation of 218. Just a little bit of notation here at the end where this first number is understood to always be the mean and the second number is understood to always be our standard deviation. Now the question we're asking is what percent of students have between a 720 and 900 on the SAT? So the way we would write this out mathematically, we would say x is less than or equal to 720 but less than or equal to 900 at the same time. So that is the situation of what we're dealing with and how we'd write that out. Now, how do we deal with it from there? Well, the thing we need to do, and we got to remember that if we can take a normal distribution and we can standardize that normal distribution, then we can use our Z tables to answer questions for us. So that's what we're going to do here. We're going to take this first one here. And remember, we can do anything we want to an inequality as long as we do it to all places and we maintain the inequality. Right, so I'm going to subtract the mean from both sides, from all three sides actually, and then I'm going to divide by the standard deviation. Okay, so I got 720 minus 110 or 1010 divided by 218, and that's going to be less than or equal to x minus 1010 over 218, and that's going to be less than or equal to 900 minus 1010 divided by 218. Now, this center piece here, the one in the middle, that's Z. So now we're going to get a Z-score on the left and we're going to Z-score on the right. You do a little bit of mathematics here and you discover that the one on the left here is negative 1.33, just simply doing some subtraction and division there. On the same thing on the other side, but we get 0.50 on the other side. So what does this mean? What can we do with this? Well, now what we need to do is we need to actually get out our Z-score table and use that. So I actually have one here. I'll just post it. Okay, so I've posted that here, and this is my Z table. Now, the way we read this is that going across, we have these known values. So let's just say that we're talking about one of our values here is negative 0.50. So negative 0.5 is right here, and then right going across this way are just additional pieces. Like here is 0.00, 0.01, 0.02, and all the way across till we get over here to 0.09. So if we were at 0.59 and then we went to 0.5 or 0.6, 0.6 would be the next piece, 0.0 or 0.59 would be that piece. Here we're dealing with 0.5 negative, right? So there's that value right there. So now we know the value that we need is 0.3085, right? There's that one right there. Now, the other one we need is negative 0.33. So negative 0.33, well, here's 1.3, negative 0.13, but we don't have the other 3 up there. So we'd go negative 0.33 is that one right there, meaning this is 0.0918. Okay, now I can run through that process again real quick just to kind of explain in a little bit better detail. Maybe now that you've seen it one time, you can always hit pause and rewind as well. But the idea is we're finding this value along the leftmost column, and then if there are additional decimals after that first location, that 10th location, we're then going to use those across this way. And that's just really as accurate as this table can be. Okay, so negative 1.33, we go to negative 1.3, and then we identify across the top where the 0.03 is, and we'd add that to it, which gives us the 3.3, and that's that value right there. Now, what does this mean? Well, this is a place where knowing what the standard normal curve looks like is extremely useful to us. So it looks something like this, right? with this right here being 0. Okay, that just kind of gives us a place to work here. So here's z equal to 0, all right? And then here would be z equal to negative 0.5. And over here would be z equal to negative 1.33, okay? Now, how do I know that? Well, because to the left of 0 is going to be negative, just like it is with our number line, okay? So those are the values. And this isn't necessarily drawn to scale very well, but that's okay. What did these values up here mean? Well, these values up here, one way to think of this is it's the area, the cumulative area under this curve up to the value of negative 0.5. This other one is the cumulative value up to 1.33 on there as well. So this is a cumulative area under that curve. Another way to think of this is this area represents the percentage below. Okay? Or this percentage, and maybe you don't want to think about this in terms of below. Maybe you want to think of this as the percentage to the left of that location. So this would be the percentage to the left of that location. And when we say percentage, this percentage is understood to be the area between that curve and the x-axis, okay? That's less important than realizing or understanding that we're talking about percentage in this particular instance, or the proportion, okay? So we're saying that the percentage below here is negative 0.0918. And that makes sense because this space right here is going to have to be less than that right there, because the other one here, I'll use red and I'm going to go the other direction this way. All right, that area right there is 0.085. The blue section, just that little piece right there, is 0.0918. So if we want to find the area between, which is what we're wanting this little green space right here. Okay, we want that. We're going to do 0.3085 minus what's below it, right? Which would be 0.0918. And that gives us a total of 0.2167, all right? Which roughly translates into about 22%, all right? So roughly 22% of the population has between a 720 and a 900 on the ACT, or the SAT rather, okay? And that's how we can use this to answer questions. Now, why would we care about that? Well, maybe this is actually really important in college athletics. If we want to know how many people are eligible to play college athletics, there's actually a kind of a sliding rule they use based upon ACT score or SAT score and your high school GPA. And based upon those two pieces, it determines your eligibility to play college ball. And so here what we're saying is that 22% of the population has between a 720 and a 900, which severely limits the number of people who would be eligible. Now, the thing is that you can always go above that, but 720 or 900s are cutoff numbers, and that's why we're focusing on that. 900 on the SAT essentially means that you kind of have an open shot at getting into playing college athletics. I think it correlates to like a 2.3 GPA. In a 720, you have to have a 2.75 or something like that to get to play college athletics. So these would be the two kind of cutoff values. And anything above a 900, it starts to get easier and easier to deal with that sliding rule, so to speak. But this is the percentage of people who lie in that realm. So you're not really talking about a huge chunk of the population. You're talking about less than 25% of the population. And when you're talking about athletes, you're talking probably even a smaller percent of the population on top of that, because a lot of these people who taking the SAT are not going to be college athletes. It's a very small percentage of the population. Normally you're speaking 10% of college-bound freshmen are going to go play athletics. So this is a very small piece of it. But this is a way that we can talk about this, and we have an idea of how many students we're talking about. Roughly 22% of our population might be falling into this realm. And that's how we can use z-scores to answer questions and use that idea of the cumulative effect of them to help us with that process. I hope you enjoyed this. I hope this was useful. Please reach out often and quickly with questions as you have them. Have a good day and take care.